Alright, so starting to look at the last section, here's the table on page 265. It has the electronegativity numbers, so if you remember, elements that are on the right side are going to attract electrons, so they have a higher electronegativity. Fluorine is the most reactive nonmetal. It has the highest electronegativity number at 3.98. If I look over here at my metals, francium is the most reactive metal. It has the smallest electronegativity number. So these are going to give up electrons very easily, and these are going to gain electrons very easily. And we talked about that in a couple chapters ago. So electron affinity measures the tendency of an atom to accept an electron. Notice on this periodic table it doesn't even have your noble gases on it. It stops with your halogens at group 17 because noble gases generally don't form compounds. Xenon was on one of the practice problems that we did. Xenon can combine with something, but it's typically going to happen in the lab, and it's going to be forced to happen. It's not going to just happen on its own. So this table, we will use this today when we're doing the little activity that we do. So if I look at the elements that are in a molecule, I can tell if it's probably ionic. I can tell if it's polar, covalent, mostly covalent, or nonpolar means that there's no charge. So water, we just looked at the bending of water. I have hydrogen and oxygen. So looking at page 265, what is the electronegativity number of oxygen? 3.44. What is hydrogen? 2.20. So if I take 3.44 and I subtract, I find the difference, I get 1.24. 1.24 falls in where on that table? Polar covalent. This would be a polar covalent charge or polar covalent bond. If I look at something from last chapter, we had sodium and chloride. What's the charge of chlorine? 3 something. 3.16. Sodium? 0.93. If I subtract that, what do I get? That one's not as easy for me to do in my head. Okay, so I'm going to get over 2. So obviously this is an ionic bond, which makes sense. I have a metal, I have a nonmetal. It's going to be an ionic bond between those two elements. So what happens is there's unequal sharing of electrons. So here's the vocab. Unequal sharing. We're still sharing electrons. There's not a transfer. But unequal sharing results in a polar charge or a polar bond. Bonding often is not totally one or the other. It's kind of hard to tell. And this graph kind of shows some examples. So here, percent ionic character, the further to the right I go, the more the electronegativity difference is going to be. The higher up I go, the more ionic it's going to be. So calcium oxide, metal and a nonmetal, going to be strongly ionic in character. Here, I already kind of showed you how to do this. Polar covalent bonds form when atoms pull on electrons in a molecule unequally. So the water example that I did was an example. And what that means is electrons spend more time around one atom than another. That's why it's unequal. So if I have hydrogen and chlorine, hydrogen has how many valence electrons? One. And it's going to go right here to make a bond with chlorine right there. But chlorine also has 2, 4, 6. It has 6 other electrons besides this one. That gives this atom a slightly negative charge. It has 8 electrons. Hydrogen only has 2, so this is going to be slightly negative. This is going to be slightly positive. If I subtract chlorine and hydrogen, I get a 0.96, and I can look at that on my table, and I will get that it is a polar type of bond. So the more electrons an atom has, the more likely it is to be slightly positive or slightly negative. I am not going to show that one. So if I have a covalent molecule, the molecule itself will either be polar or nonpolar. Nonpolar molecules don't have an electric field. They don't have a difference in charges. Polar molecules are going to have an electric field almost like a magnet, which is why it's called polar. North pole, south pole. These electrons are going to kind of align up. So if I look at water and carbon tetrachloride, both of them are polar. If I subtract oxygen and hydrogen, I'm going to get polar. If I subtract chlorine and carbon, I'm going to get that it is a polar amount. But what happens in the shape is water is shaped like this. Oxygen has 8, hydrogen has 2, so this is slightly negative. This is a slightly positive end. It's not balanced. So this is going to be a polar molecule. It has a slightly negative end and a slightly positive end. In pretty much anything that's tetrahedral, I have carbon in the middle. I have chlorine, 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 chlorine. All of these have 7 extra electrons, or 6 extra electrons. My charge is going to pull away, or my field is going to go out, but it's spread evenly. So I have polar bonds, but my molecule is nonpolar. And the activity that we do today will help you look at that a little bit better. But that's the reason I have a polar molecule or nonpolar molecule is the shape of whatever molecule I'm looking at. Water is very polar. It's a polar molecule, which makes it a wonderful solvent to dissolve lots of different things. So here it's telling you water is bent, carbon tetrachloride is tetrahedral, so their shapes are different. In water, it's not balanced evenly, so I have a slightly negative and a slightly positive end. That makes it polar. In carbon tetrachloride, they are symmetrical. They're all spread the same amount. Everything is spread evenly. That makes it a nonpolar molecule. So quite honestly, this section might be the hardest to see. So here, here's my negative end. So is that balanced evenly? Cool. Is that balanced evenly? No. So that would be a polar molecule. Abby, is this one balanced evenly? Yes. It's tetrahedral. Even though in reality the lines aren't exactly straight out, it's balanced. They all go out the same direction, the same length. That would be a nonpolar molecule. Here, these are all going to go this way. Plus, I have 2 electrons there. Austin, is that balanced evenly? No. So that would be a polar molecule. So the shape is very important. If the bonds are polar, any molecule that's not spread evenly is going to be a polar molecule. Anything that is balanced or is symmetrical will still be a nonpolar molecule, even though the bonds are polar. And this is very important with solubility. I already said water is the universal solvent. You wash clothes in water. We make food and ingredients with water. Water dissolves a lot of different things. So solubility is one property where substance's ability to dissolve in another. Polar molecules and ionic substances are usually dissolvable in each because they both kind of have charges. Like dissolves like. So water is very good at getting out dirt because they both have charges. Water is not very good at getting out grease because grease is nonpolar. Therefore, if I want to get grease out of my clothes, I need to add something to my water that is also nonpolar. Soap is nonpolar. So if I have water and soap, I've got something that's polar, I've got something that's nonpolar. It's going to cover more or clean more things because it will dissolve both. And then I will stop there for a little while.